let's wait 1 more minute. I mean, you can start, but we maybe wait 1 more minute for people to get in. Hello. Right. Before we start, maybe we can see if you guys can see what I write. So yeah, it's a bit of an improvised setup, but let's try to make it work. So I'm going to write something, and you see if you can read it, and otherwise we'll look for a different solution. Okay, so first of all, this is a computational test of qubit, and I hope you can read that. If I write, hello, can you read this? Also from the very back. Fantastic. I'll try to yeah, good. So this is going to be the setup of the talk. And please, if I forget to write in a intelligible way, just notify me. As the talk progresses, I get more tired and then I forget. Good. So yeah, now the objective of this last talk, we're going to go on for until approximately 12, is to switch gears a little bit and move from the complexity side more to the cryptography part. So here you see the word computational, so this means there will be cryptographic assumptions and cryptographic primitives that we're going to use. And I'll try to make it really accessible to both an audience which is familiar with cryptography or an audience which is familiar with quantum. Hopefully I'll get the best of both worlds. But yet don't hesitate to ask questions if you have them. And yeah, just interrupt me. If we can make it interactive, it's only better. And let me mention that this is essentially a talk which is based on the work of Brakersky et al. At Fox 2018 and the works of Mahadev in 2018. But really, this is what inspired me is sort of the lecture note of Thomas Vidick that has on the topic. I can send you a link on that. And I should also thank Thomas for answering my questions patiently. And by the way, my background is mostly classical and I'm mostly cryptography. I don't know anything about physics. So, I mean, you can ask physics question, just maybe someone in the audience will have a better answer for you. So we really are going to look at the mathematical side of things. And we're not going to worry too much about the physical meaning of things. So we're going to take the axioms as they are, and then we're going to see what we can do with it. Good. So the broad objective of this computational test of qubit is the following. So we have a prover P and a verifier V that run an interactive protocol, and there is some quantumness in the head of the prover, but the verifier and the computation and the communication is entirely classical. This is all classical. Classical, yeah. And at the end of the day, we want the verifier to output a bit, either 0 or 1, that determines whether the verifier was convinced or not about the fact that the prover is a qubit in his head. Okay? So it sounds like a bit of an esoteric task, and it's, at this point it shouldn't even be clear what does that mean. And the goal of this talk is to sort of gain an intuition on how we can do that. In principle, it's even unclear that we can do this at all, but as it turns out, we can. Good. So let me give you a brief summary of what we're going to see. So the first point, we're going to define a qubit. And of course, you all know that a qubit is a unit vector in a Hilbert space, but we're going to give a definition which is slightly different than that. And well, the operational meaning of this definition, why will we adopt this definition, is because something we can test. I mean, it's hard to test, if someone as a unit vector is on Hilbert space if you cannot directly operate on the Hilbert space, right? So the verifier really, just think of it as a classical machine. So it doesn't have access to the exponential amount of dimensions of the Hilbert space. So, oops. Okay, so the second point is going to be to define our cryptographic tool. So we're going to introduce some cryptography, and this is going to be called trapdoor claw-free functions. In short, it's TCF. And I'm going to say what this thing is, and I'm going to maybe, if I have time, give you a little bit of intuition how we can construct that. Afterwards, we're going to describe the protocol, and of course, analyze it. And depending on how late are we, the analysis will be more or less formal. Good. Any question before I start? Okay? Good. So before defining a qubit, I want to recall what the definition of an observable is. And we're going to define, this is going to be useful for defining our qubit. It's going to be like sort of an operational definition of a qubit. But so let me just define what a binary observable is. Binary observable. Right, so a binary observable is a matrix O defined as the sum of two orthogonal projectors times their eigenvalues. So our observable will be, oops, and I'm going to, will be P0, sorry, lambda 0, P0, plus lambda 1, P1, where P0 and P1 are just two projectors, and it holds that P0 plus P1 sum up to identity. Okay? So this is our definition of observable. Again, if you like, you can think of these objects in 2 dimensions, right? These are just 2 by 2 matrices, but you don't have to. This is like a general definition, and we're going to see an example later. And the way to think about this, these eigenvalues here, lambda 0 and lambda 1, this is sort of a label that we're going to assign to a particular projector. So when such a projection succeeds, we're going to return the value lambda 0. Sorry, that was P0. Whenever P1 succeeds, we're going to assign lambda 1 to that particular value. So, if your linear algebra is a little rusty, you should just really think of that as being labeled. Of course, they are. I mean, if you're familiar, those are just the eigenvalues of those projections. Right, and throughout the course of this talk, we're always going to assign lambda 0 to be lambda 0 to be plus 1, and lambda 1 is going to be minus 1. Maybe it's a little awkward, but if you have worked in the Fourier basis, you understand this choice. But anyway, let's just think of this as just P0 minus P1. So this is our definition of the observables. Okay? Good. So what are the properties that we're interested in, right? So let me define first a useful quantity about these observables. So an eigenstate of the observable is a vector which is unchanged by one of these projections. Okay, so the first quantity that I'm interested in is to look at the eigenstates of this observable, right? So for example, if I have psi 0 such that P0 psi 0 equals psi 0, then this is going to be an eigenstate of my observable because it's unchanged by the projection P0. And in this case, well, since the labels that I'm assigning, so the eigenvalue is plus 1, the eigenvalue of this eigenstate will be plus 1. And on the other hand, psi 1 is going to be such that P1 psi1 is again psi1. Okay, these are useful quantities, the eigenstates of my observable. Okay, a useful property of observables is that of binary observable. So first of all, in general, we know that observables are Hermitian, right? What does it mean? Well, it's a symmetric matrix which is its own conjugate, right? So we know that O dagger equals O. And you know, if you take an observable the way I defined it, namely as a sum of two orthogonal projectors, it's actually not hard to see that actually squares to identity. So this is, you know, maybe you can calculate this offline, but if you don't believe me, but it's pretty easy. It's an elementary calculation. The way I define the observables is just squares to identity. So this is going to be a factor we're going to use over and over. Okay. So let me just define one more property. Well, it's not going to be a definition, but rather a way to compute an expectation of an observable. So given a state psi, the expected value of O is given by the following formulation, right? So before I tell you what this thing is, again, the operational way to think about this is I'm applying this observable on a given state, and depending on which projection will succeed, I will get a different outcome. And the outcome are these two lambda 0 and lambda 1 labels. And if I care about, you know, the expectation is the value that I get of the sum of lambda i's times the probability of that event occurring, right? So let me just write it here. It's going to be just for us just a sum with two terms, but in general this thing is going to be sum over all labels. This is our eigenvalues times the probability that projections 1 succeed on the state psi. And again, recall that the projections are just the terms that sum up to our observable. And I'm going to just do this calculation once, so that so this is sort of the probability that things succeed, and this is our label. Okay. I'm just going to do this calculation once, so that we're happy. But yes, this is just algebra, so there's nothing particularly insightful happening here. Okay. So what is this? Well, this is just, oops. This is just lambda I times the trace of pi I psi, and you know, by linearity, I can just write the trace of sum I lambda I times pi I psi, and well, now this is actually my observable, right? Because it's the sum of orthogonal projectors. So this is actually, well, if you just do the calculation, you can, you know, take out the diagonal terms, and this is what I end up with. So this is how we compute the expectation of an observable on a given state. Okay? Good. So now that I introduce observables, I think it's a good moment to take questions if you have. Now, some of you may not have seen what an observable is, but this is sort of going to be our main handle to define a qubit. And the reason why we, you know, observables are a better quantity to define a qubit for our purposes is that observables literally mimics something that you can classically observe. Like, so that, you know, sort of the, maybe if you're doing some experiment with your state, the statistics that you get out of your experiment. That's sort of the gist, right? So this is like a better way to define, and a way which is like amenable to a classical protocol. Okay? Good. Questions up to now? Great. Now, I'm going to give you a definition of a qubit based on the existence of certain observables. And then I'm going to sort of justify this definition, and then we're going to proceed with the rest of the talk. Okay? Good. So let me proceed with my definition of a qubit. Right. So the definition, I'm going to define a qubit as a triple. A qubit is a triple psi x comma z such that psi is a unit vector in some Hilbert space. Okay, so H is our Hilbert space. And X and Z are going to be our observables. So X and Z are observables on H. And again, recall what observables are, matrices that act on the appropriate space, which are the sum of two orthogonal projectors times their eigenvalues, their labels. Okay. So far so good. This is like the what we expect. And now, yes.
Are you restricting the dimension of H here?
No, we're not restricting the dimension. So good. Yeah. I wanted to touch upon that point later, but the point is that if we want to think about what we're going to use this for, there is no way that we can tell what's the dimension of the Hilbert space that the prover is operating. We don't know what's happening in the prover's head, right? But there's going to be a sense whether all finite dimensions are going to be as good as like 2 dimensions, like a standard qubit dimension, and I'm going to talk about that right after. Okay, so far so good. There is nothing currently. There is nothing special about it. So we have to sort of constrain, to give one more constraint on the behavior of these two observables. And well, what's the defining of behavior of quantum mechanics? The defining behavior is that these two observables are so-called mutually incompatible. So what does it mean? It means that if I know exactly, if I know exactly for a given state what's going to be the output of a particular observable, then if I take the other observable, the state should be completely indeterminate by that observable, right? And if you are familiar with the basics of quantum computing, maybe just a good analogy would be like a measurement in a computational versus in the Hadamard basis, right? So in that case, it's clear that if your state is a computational basis state, so it's like completely in one of the two axes, then measuring that in the Hadamard basis will just be completely undetermined, meaning like it will give you plus or minus with probability exactly a half. Okay. Good. And I want to convince you that sort of like the right way to capture this mutual incompatibility, which is sort of really the essence of what allows us to operate on a qubit, is this notion of anti-commutation, right? Which I'm going to define now. So X and Z anti-commute. So what does it mean? It means that, anti-commute on psi. What does it mean? It means that, XZ plus ZX times psi equals 0. I guess you should think of this as, if those are like two dimensionals operators, this is a 2x2 matrix again. Okay. Sorry. Good. Well, so the questions up to now? Right, so this is the definition of anti-commutation. Well, I mean, by linearity, we also have that. We can rewrite this as xe on psi equals minus zx on psi. Okay, so that's why it's called anti-commutation. So let me sort of justify this definition a little bit. So for example, if we take psi to be an eigenstate of x, so in particular it means that it's completely determined to the observable x. I mean, of course, we have to assign one label, and without loss of generality, we are going to say that is eigenvalue, so the label, so the output of the observables is epsilon with eigenvalue epsilon. Well, then let me just plug this psi in my expression above, right? So I know that 0 equals to psi xe plus zx psi. Right? So, well, since X is a Hermitian matrix, and again, by definition of psi being an eigenstate of X, means the application of X on psi leaves psi unchanged, except that you pick up this factor epsilon, right? So this is just really epsilon times psi z plus c, which is just 2 epsilon psi z psi. So this in particular means that this is going to be equal 0, right? So where am I going with this? Well, this essentially means that the expected value of applying z, right, on my state psi is 0. So it means that it's going to be with a half probability plus 1 and with a half probability minus 1, which is exactly what it means to be completely indeterminate with respect to that particular operator. Okay? So this is something that sort of justifies that definition. And why does this mean? Why this is a good definition of sort of anti-commutation and being mutually incompatible? Any question up to now? Good. Well, if you want to think about geometrically, you can think of just that state making it like a 45-degree angle with a given particular observable once it's completely determined from a given observable. It's good. So one thing that I slightly cheated about is that's the sort of the ideal relationship that we would like to verify, but the actual relation that we will be able to verify is not an exact equality, so we won't be able to check that this is going to be exactly 0, but what we'll be happy to is that this relation will be somewhat close to 0. I think that's sort of the best that you can hope for from a classical experiment, because again there's going to be some randomness happening, so with like a certain probability your experiment will fail. But this is even slightly worse in the sense that this is going to be true only for computationally bounded attackers. So that's because we're going to use cryptography, right? So there's going to be always a chance that you're breaking your cryptographic primitive and thereby passing the protocol without actually having a qubit in your head. Okay, so really that's going to be the gist, right? We're going to say, we're going to take the protocol, define a given state of a prover at a given point in time, and say, well, either the prover has broken some cryptographic assumption, or we can define a particular unit vector in a Hilbert space and two anti-commuting observable on the same space, which satisfy that relation. Okay. Good. So, right. So maybe this is a something that I want to. Oh yeah. So maybe let's be very concrete, maybe for the quantum expert this is going to be a bit trivial, but let's just go through the math once, and let's see an example of an observable. So the most well-known observables are the Pauli observables, which are these 2 by 2 matrices. This is sigma x and sigma z. One, zero, zero, minus 1. Well, what are these things? Let me just do it for sigma z. Well, this is just, this is just like the sum of 2 projectors. So the projector that projects onto the first coordinate, which is just this, right? And the projector that projects onto the second coordinate, which is just this. And now, of course, I have to plug in the eigenvalues that I selected at the very beginning. So this is going to be a plus, and this is going to be a minus, right? So you can verify that this is what gives you. And this in particular, again, operationally, what this thing is just a measurement in the computational basis. If you think about it as operating on a particular qubit, this is just a measurement in the computational basis. Whereas our other operators, I'm not going to expand it here, is just a measurement on the Hadamard basis. And you can check for yourself that these are indeed mutually incompatible. In particular, they satisfy the anti-commutation relation that I defined before. Okay? Good. So, and this is sort of like you should put us in a good place, right? It says like at the very least, the formalism that we introduced before makes sense for the kind of observables, canonical observables that we're used to. Okay. Right. So, and well, the reason why I also introduced these observables is that it's a little bit more than just a sanity check, but it's really to motivate sort of the fact that we can actually don't have to restrict ourselves to a two-dimensional qubit, which was brought up earlier. And in particular, what we can show is that there is a sense in which any 2 anti-commuting observables on a given Hilbert space, they are isomorphic to these 2 particular observables. I'm saying isomorphic, quote unquote, because it's that's not exactly the relation that they satisfy. So the exact relation that they satisfy is that there exists an isometry that sort of maps the behavior of any 2 anti-commuting observables on a given particular Hilbert space to these 2 particular observables on a 2-dimensional space. Okay, and visually, what's happening is that this is like a nice picture that I stole from Thomas's notes. Is that you start from your Hilbert space H, that's the Hilbert space that we're operating in our definition. So that's the most general definition, and our observable X and Z, they act on this Hilbert space. So they take some unit vector into this Hilbert space and move it and rotate it to some other unit vector in the same Hilbert space. But an alternative way in which you could operate, you could apply an isometry V. Does everybody know what's an isometry? So an isometry, for those of you who are shaking their head, an isometry is just a unitary on a larger space. So it's like maybe, operationally, again, just think of it as adding some register and then applying a unitary. And this is important because our spaces will have 2 different dimensions. So our isometry maps this Hilbert space H to a different space, which is C square tensor some other Hilbert space H prime, and we have the property that on this Hilbert space we can apply our observables that we defined earlier, sigma z, sigma x. Of course, they act only on the first register of this observable. So we have to say that they do nothing on whatever the rest of the state is, which is going to be this H prime, right? So we just tensor with identity. And I'm going to be a little bit sloppy here. I'm just tensor with identity, meaning do nothing on H prime, okay? And again, this is well, these are operators, these are Hermitian operators, so they map to the same space. And now the point is that the same isometry sort of mimics the operation that we're doing on H on this other space, right? So this essentially tells you that there are two ways to obtain the same thing. So in particular, one is to apply the isometry and then apply our Pauli observable on just the the first register of a given state, and the other is to apply our observable x and z on the original Hilbert space H, and then apply this isometry, and you obtain the same thing. Okay, so there's like sort of this nice parallel, and this tells you that these two observables are in some sense equivalent. Okay, so this is all I want to say, and this the whole objective of this thing is to sort of convince you that the definition that I gave you of a qubit, let me just quickly recall it, which was this one, right? So that the psi is a unit vector on H, and then there are these two anti-commuting observable, is the good definition, like is what we intuitively want, right, from the definition of a qubit. Okay. So yeah, and I'm very happy that I established this formalism, so I can sort of move on with the talk. And the next I'm going to move to the crypto part, and then we're going to look at the protocol to establish this particular guarantee. So if you have you have some questions about the formalism, now it's a good time.
Would you allow density matrices instead of pure states of psi?
I guess so, yes. I mean, we won't do it here, but you could allow density matrices. One thing is that with proofs, you can always, whenever you're constraining the prover of a given machine, the behavior of a certain machine, you can always say, well, the best this machine can do is to take the particular pure state which has the highest success probability. So we're always going to, in our protocol, we're always going to assume without loss of generality that the state of the machine is going to be a pure state.
You can also purify the density matrix, I guess, because you're not restricting the dimension of the...
Yeah, absolutely. Thanks.
Does V need to be efficiently implementable here?
No, it's not. It doesn't need to be efficiently implementable. But like for this particular case, it is going to be efficiently implementable.
I seem to have missed it. Did you define a test for a qubit?
So the protocol?
No, did you define what completeness and soundness are for this?
No. I just defined what a qubit is for the moment.
So we're going to see that later.
Yeah, we're going to see that. Yes.
Okay, you show a definition for a qubit, but I guess this generalizes to, if I want to define 3 qubits.
Yeah, it generalizes in a nice way. Yeah, so there's a way in which it generalizes. Of course, I mean you can, take more than 2 observables and then show, define that they satisfy the Pauli anti-commutation relation. Of course, you can do that, but it's actually. Yeah, for now you have to sort of, so that's maybe like one definition you can propose, but then the question is, can you prove that, that it satisfies that definition? And I think like it's going to be a little bit tricky once you move to a qubit. We're not going to see this here. We're just going to stick with the test of 1 qubit. But okay, short answer, in principle you can do that, but there turns out to be like some technical hurdles for which we are not going to be able to prove exactly that. Yes.
You underlined the ones. Is it a Hadamard matrix or what did it notify?
I cannot hear you very well. Sorry. Could you please?
The one is underlined in your example.
Underlined.
Or is it only your handwriting?
So you mean H?
The one and.
Sorry, I cannot understand.
I think it's just the handwriting. I think this is how we practicing one.
Is it a 1 and the line below? Above.
Above? Oh, these 2 things. No.
Okay. Yeah.
Oh, this is a 1. These are 0. 0.
Yeah.
0,
Okay.
0.
The underline doesn't say anything. Okay. Thank you.
It's a 1. Sorry.
Thanks.
Okay. Apologies for my handwriting. Good. More questions before we move on. So again, this is just the formalism. We've just defined what a qubit is, and now we're going to test, right? So that's. But before going to the protocol, I have to sort of introduce the main tool that we're going to use in this protocol, which is going to be the Traptal-Claw-Free functions. So TCF. And what is a TCF? Well, a TCF is just a pair of functions. For technical reason, we need sampling algorithms. So this is like a pair of functions f0 and f1, which are output by some sampling or some generation algorithm that takes as input the security parameter and outputs these two functions. So technically, this is a family of functions. If you don't know what the security parameter is, it's something we use in cryptography, but maybe it's best not to think about it. So we just, just think of it as just two particular functions uniformly sampled from a certain family, and the security parameter is sort of used to get meaningful statements about the asymptotic hardness of things, right? So you want things to be hard as the security parameter grows, but again, like I don't want to be too pedantic about this in this talk. So let's just think of them as two functions, and I'm going to define f0 and f1 to map, from a given domain to a particular range, and I'm not going to define exactly what these things are, except that I want it to be efficient to sample from the domain of the function. So if you like to think about binary strings, that can be our domain. So we're going to require some properties from these functions, okay? So the first property is that these functions are exactly 2 to 1. So exactly 2 to 1. 2 to 1. So what does it mean? It means that for all y in the range of the function, there exists exactly a pair x0, x1 such that f0 of x0 equals f1 of x1 equals y. So what does it mean? This means that if I pick a given element in the range of this function, there exists exactly 2 preimages for that particular element. Okay, so exactly 2 for all elements of the range. Okay, good. So this is the first structural condition. The second structural condition is the existence of a trapdoor. So there exists a trapdoor.
Sorry, did you mean the functions to be the same, or when you say 2 preimages, you mean for the same function?
Oh no, for each element of the pair. So literally what I wrote here. So
Okay, so that's correct. Okay.
yeah.
Does the same f0 and f1 are 1 to 1?
Yes, correct. Yeah. So good. So the pair is 2 to 1. F0 and f1 individually are 1 to 1. Correct. Oh. Again, okay. So this is my definition. I'll state the caveats later. But I think we can think about it like that. So there exists a trapdoor. So the next condition is that there exists a trapdoor TD, which is sampled together with the function families, for which, if you're given this trapdoor, you can invert this particular any element in the range. In fact, right? So if I'm given y, there is an algorithm invert that is takes as input the trapdoor and whatever y it is, and returns x0 and x1, which are the preimages of the y. I mean, of course, you need the trapdoor for doing that, but we assume that if you're given, you can do this inversion operation with probability 1. Again, for simplicity. Good. And then, of course, like I haven't said anything cryptographic about this object, but the sort of the security definition that I wanted to achieve is the so-called adaptive hardcore bit. So let me just write it in big letters. Adaptive hardcore bit. Hardcore bit property. And at first it will look a little bit weird, but I think hopefully it will make sense why we require this particular property. And remind me later to tell you why this thing is called claw-free. I typically forget to say that, but I should clarify the name. Right. So you know, in cryptography, we like to define things as success probabilities of an experiment. So we define these properties as to hold if for all efficient adversaries, the success probability on a given experiment is going to be, you know, reasonably close to zero, negligibly close to zero, if you know what I mean, but if not, doesn't matter. So we sort of define properties operationally. So we have an experiment, and we say, well, you know, there exists no machine that wins this experiment with probability, like substantial probability. Okay, so I have to define what the experiment is now, right? So I'm taking a given machine A, and by machine I mean, you know, any algorithm, like any circuit, any algorithm. Take your favorite computational model. Of course, A is going to be a quantum machine. So in particular, we can give it even a state psi if we want, like an auxiliary information, if we like to define security like that. We are going to sample to a pair of functions together with the trapdoor. So this comes out of the generation algorithm. Again, I don't want to write exactly the security parameter, but it's there. And we're going to send these two functions to the adversary. So we're just going to give these two functions to the adversary. And the objective of the adversary is going to be to return a given xb, so one particular preimage, together with a string d. And I'm going to make precise when the adversary wins, okay? So now all I have to say is like, what's the condition for this adversary to win? So we say that A wins if the conditions are satisfied. So the first condition is that xb is indeed a valid preimage of one of the two functions, right? So this is like sort of the first non-trivial thing to say. So that f of fb of xp equals y. So it's in the domain of a particular function. So x is to be like a particular preimage. And one simplification that I'm making is that when I'm looking at a particular preimage, I'm allowing myself to sort of say this is either a 0 or a 1 preimage, right? And maybe you can think of having this bit 0 or 1 sort of encoded in the bit. So maybe you can think of xb being of the form b concatenated with something else. I don't care. Like I'm just allowing myself to sort of, I'm looking at a preimage and I'm able to tell whether it's a 0 or 1 preimage. Okay. There was a question there.
Where does the y come from?
Oh no, it's just like there exists a y such that. So yeah, so xb is in the domain of one particular f. Good. Now the second condition is the tricky one to define. So first, to define the second condition, first I have to use the inversion algorithm to sort of recover both x0 and x1 out of this y that I sent earlier, right? So I'm going to define x0 and x1 as an invert. And for this I need the trapdoor. And I'm going to say that the condition is going to be that, first of all, this string d is non-zero. And the maybe trickier condition to define, I'm going to write it down and then discuss it quickly, is that the inner product of d times the bit decomposition of x0 XOR the bit decomposition of x1 is equal to 0. Okay, so this looks very, very complicated, but it will make sense in a second. Good. So, right, what am I requiring here? So first of all, I'm requiring the adversary to send a valid preimage. So this is easy. And then I'm asking the adversary to return a string d, which is orthogonal to this vector here. Now, this vector is taking, is calculated by taking a particular preimage x0 or x1, computing its bit decomposition. This is something I can always do, right? And then XORing it with the bit decomposition of the other preimage. okay? And this defines a binary string, right? So I'm taking, I'm taking a vector, any vector, which is orthogonal to that particular bit string, okay? Now, why does this intuitively make sense, right? So if this is sort of already reminiscent to what's happening if you are computing a Hadamard measurement on a particular superposition, right? So imagine if you had a superposition of x0 and x1. So what is the effect of measuring that particular superposition in the Hadamard basis? Well, it will be, so first of all, the Hadamard is like just the QFT modulo 2, right? So the QFT over F2, right? So it's going to return a bit decomposition of these two particular elements. And then if you do the calculation, you will see that you will really obtain a particular vector which is orthogonal to the XOR of these two particular strings. Okay, so this is a bit of calculation, but you can verify it for yourself. And maybe, like maybe the even higher level overview of this is that this particular condition will correspond to a computational basis measurement, and this particular condition will correspond to a Hadamard basis measurement, like on a very high level, right? So, and it's going to be hard, right, to return these two things simultaneously, which will, in some sense, says that these two things, these two particular measurements will anti-commute, because you will not be able to, no efficient adversary will be able to produce these two particular string with high enough probability. Okay, yes?
So is D a real vector?
Oh, it's a binary vector. It's a 0-1 vector. Everything is over F2. Yeah, thanks. Yeah, thanks, actually. Yeah. Thanks for reminding me. This is a 0-1 vector. Make sense? Good. Any more questions? Yes?
Why is this called adaptive hardcore-based?
Good. Right. So I mean, if you're a little bit familiar with cryptography, you know that like a thing called R-Corbit is just, the Goldrake-Levin R-Corbit is just like the inner product of a random string with a particular preimage, right? This is called adaptive, and sort of the inner product is sort of reminiscent to what's happening here, right? Right. This is like you have to return like some particular string such that its inner product is actually 0. So, if I had no choice about what X to do this particular operation on, then it would be very similar to Goldrake-Levin, because what Goldrake-Levin tells you is that it's actually hard to predict this inner product, right? But here it's called adaptive because the adversary sort of has a choice on which particular on which particular image being tested on, right? So the adversary can choose the XP, right? Can choose that particular Y, right? If it was not adaptive, it would mean that I'm giving you sort of a random Y, and you have to return a D orthogonal to this bit representation of the preimage of Y. That's why it's called adaptive. Yeah, great question, by the way. Yes. More questions? Okay, we are doing great with time. So, good. So, okay, let me comment a little bit on this primitive. And the thing that I want to say is that this is called claw-free. And why isn't it called adaptive hardcore bit trapdoor function? Well, the reason is that this was studied, this kind of primitive without the adaptive hardcore bit property was already studied in cryptography many years before this sort of protocol came out. And you can think of adaptive hardcore bit as like a strengthening of claw-freeness. In particular, if claw-freeness would not hold, it would mean that I would be able to sort of find a claw. Well, a claw is just like a collision, right? It's a pair x0 and x1, right? If I'm able to find such a claw, then of course I can compute this thing myself, right? And then obviously it's easy to find a vector which is orthogonal to that particular operation, right? So this sort of tells you that adaptive hardcore bit is a strengthening of this property. And I'm not aware of any result in the other direction. I don't think, I don't know what was the belief, but I don't think there is any explicit reduction in the other direction. So one direction is obviously trivial, the other direction is unknown. But that it is what it is. So this is called claw-free, trapdoor claw-free functions. Okay. Good. So does this thing exist? Like the question, of course, is like, you know, I define this particular property, but can we actually realize this primitive? So it turns out that the answer is not exactly, but there exists a scheme which is good enough. And this is, I'm not going to say much about this, but like there exists a TCF from the hardness that you can prove that is adaptive hardcore bit, assuming the hardness of the learning with error problems. So the learning with error problem is sort of like the bread and butter of post-quantum cryptography, right? So in short, LWE. And when you see LWE, in the post-quantum context, you're always happy. Like you see LWE, it's a nice assumption, good. We're happy with LWE. What we're not so happy about is that, I mean, everything in the end works out. It's just like the way I define it, TCF it's a way simplified primitive. It's not you don't get exactly this with LWE. In particular, there are two simplifications that I made. So first of all, this property of exactly 2 to 1 doesn't hold, and you get something a bit weaker. It just says that you can think of it as like overwhelming 2 to 1, right? So if you pick a particular y in the range, that with overwhelming probability will be 2 to 1, so you get like a little bit of an error there. But like sort of the real problem is that well, it's not a problem, but sort of the real difficulty that makes things significantly more complicated is that these are not actually functions. So these map to distributions. So these are, or maybe another way to say it is that it's not a deterministic function, but it's sort of a randomized function, right? So you don't get to define this nice range, but this is going to be like a distribution of the function. So that makes things a little bit more technical, but you know, I think like for conveying the ideas, the main ideas of the protocol, it's just enough to sort of think of this as just functions. So we have like this well-defined range and domain. We know we can sample from the domain. We have this exact 2 to 1 property, and we know that that they satisfy this adaptive hardcore bit. Okay, so that's what I'm going to go with. Okay, so next, so we now have all the sort of the material in order to you know, state and define and analyze our protocol. Right. So now next I'm going to sort of describe the protocol and just give you a high-level overview of the analysis. And yeah, if you have questions, I think now it's also a good moment. If not, I'm going to go on with the protocol. Okay, so the protocol is obviously an interactive protocol, and it's a protocol between the prover and the verifier. And the prover is quantum, right? And you know, so let's see what the protocol is. So the prover and the verifier. And it's an interactive protocol, and as I said, at the end of the interaction, the verifier has to sort of output a bit 0 or 1, whether it's convinced that there is something quantumly happening in the prover. So that's sort of the gist. And more precisely, now that we define what a qubit is, well, we have to be able to say, well, if a prover succeeds in this protocol, then there exists a well-defined qubit inside of its state. Okay, that's sort of what we're going to go with. So the first part of the protocol is that the verifier sends 2 functions, or a trapdoor-claw-free function pair, F0 and F1, sampled from this generation algorithm. And of course, this generation algorithm also returns a trapdoor, but obviously the verifier won't give the trapdoor to the prover, otherwise it would be just used to invert, right? So it just keeps the trapdoor for himself. Now the prover creates what? It creates a uniform superposition over all possible pre-images and over all possible images of a given function. So what is this? Well, this is just sum over all x. X. Hopefully I didn't screw up. F b of x. Of course, sum over all b as well. Okay, can you see this? Good. So what is this? Well, this is just a uniform superposition over all possible x in the domain together with the result of the function fp applied on that particular f. Okay, so this is something I can efficiently compute. I won't show it here, but like maybe you can trust me that this is a state which is efficiently sampled by the prover, and it doesn't need to know the trapdoor, it just needs to know the description of the functions f0 and f1. okay? So next, what the prover is going to do is going to measure this particular register, so apply a measurement to this particular register here, and this will collapse to a given, to a particular y, okay? So what's this going to be the state of the other register? Well, is essentially everything which is consistent with the observation that you made in the second register. And what is that? Well, we know that the function is exactly 2 to 1, so that's going to be a perfectly uniform superposition over the two preimages of y, right? So this is going to be just a x0 plus x1, and I'm normalizing it, but I'm sure I'll forget soon to normalize things. Good. So that's what the prover obtains. Just a uniform superposition over the two preimages of a particular y. So, by the way, this is the behavior of the honest prover. So I'm just describing the protocol, how it's supposed to be run. Of course, the malicious prover would do arbitrary things. We don't know what the malicious prover will do, right? Good. So the next thing is that the prover will send this particular y. You know, it came out of a measurement, so you know what this y is. You have a classical description of it, particular element from the range of the function. And at this point, the prover is going to sample a bit, a challenge bit from 0, 1. And if c equals 0, what the verifier is expecting is a particular xb, which is a preimage of the y that the prover committed in the round before, right? So this is going to be fb of xp equals y, where the y is fixed at this point, okay? Again, I'm simplifying a little. I'm assuming that if I'm given an x and I can tell whether this is a 0, 1 preimage, so I know which f to apply, okay? So this is what we want if c equals 0. And well, how do we get it? How does the honest prover get such xp? Well, it just measure the register here in the computational basis. So, and that will just return a random either 0, 1 preimage of y, okay? Good. Whereas if c equals 1, then, well, I guess at this point you might have guessed it, then the prover is expected to return a particular d, which is a string in 0, 1 m. Well, and then the check of the verifier on this particular string will be, so first of all, it will use the trapdoor to invert y. He will invert y with a trapdoor. It's horrible. Let me try again. Trapdoor, comma, y. So this is just to sort of define the verification check. Well, now that I have this two preimage, I can check whether D is indeed a vector which is non-zero, so it shouldn't be the all-zero vector, and it's a vector which is orthogonal to, again, over where the inner product is over F2, over the bit decomposition of X0 XOR the bit decomposition of X1. Right, so, and if this is equal 0, then I'm happy, then I accept. Okay, right, so note that in order to compute this predicate, in particular, in order to compute this string, I need to know the trapdoor, but I better not tell the trapdoor to the prover, otherwise it can, sort of invert and do the same, okay? And again, well, how does the honest prover obtain this particular D? Well, it can just measure the same register, right, in the Hadamard basis. So if you do the calculation, that's exactly what you obtain. Like you just do the Hadamard, QFT over F2, right? And then measure that measure that, and you will get a uniformly sampled D such that it satisfies this condition. Okay. So now it's sort of nice because this really aligns well with the guarantee that our TCF tells us, right? So in particular, now I'm sort of skipping ahead a bit of the analysis, but like just to give you an intuition, if the adaptive hard-coded property allows us to establish that the prover cannot succeed with noticeable probability in both tests. So, you know, if it prepares a given state, it will only be able to succeed only in a given test at a time, right? So, which means that these two, the observables defined by these two particular tests are indeed mutually incompatible. Sorry, right? Did that make sense? So, I mean, of course, the prover can succeed on both, but exactly in one of them. So it can't just succeed on C equals 0 and subsequently on C equals 1, right? So once he made up his mind on the measurement that he wants to do on the particular register, then he's sort of stuck to that decision. He cannot sort of go back and answer to the other challenge. So that's sort of the intuition. Okay? Question? Yeah.
How we can get D? I mean, how does the prover send the D over here?
So the D is essentially what you get by measuring this particular register in the Hadamard basis. I mean, I can show you the calculation, but like if you believe me, that's exactly what you get, right? So the effect of sort of applying the Hadamard is to, you know, first of all, you just bit decompose because it's Hadamard over F2. You just bit decompose these two. It creates a uniform superposition, and then if you measure, you will get. And this is already good, right? Because like for one test, we needed to measure things in the computational basis, and for the other test, we needed to measure the same thing in the Hadamard basis. So this is like sort of gives us a good indication that what we're doing makes sort of sense.
I'm a bit lost about the whole model.
Yeah.
So our goal is to test whether the prover has some quantum bit in its pocket.
Yeah, correct.
So why do we care if the malicious adversary is not classical?
Sorry, what do you mean by?
I mean, okay, now we see that the honest prover somehow can win the test.
Right.
But if, so the malicious prover, what we want to know is it doesn't have a quantum bit in its pocket.
Right. I mean, by the way, not having a quantum bit is not equal to being classical. So, like, being classical is like it's a much stronger statement than not having a qubit, right? So maybe you're just doing something quantum, but you don't have.
Also, some kind of this. This sort of supremacy, but not quantum computing things, maybe.
Well, I'm not sure exactly, but like it's like a stronger statement, like saying that you can define a qubit versus saying you're doing something quantum. That's like a way stronger statement than. But anyway, like so maybe to go back to your let me try to sort of clarify the goal and sort of go back to your question. Again, so the goal here is to define a protocol such that the honest prover can pass by sort of doing the measurements in the appropriate states and like doing something which is like typically quantum, right? Just do these two anti-commuting measurements. And why do we do this protocol at all? Well, because we need to, the way we define the qubit was through these observables. And observables are like classical quantities that we can extract from, an experiment on a particular quantum state. And the protocol itself will define our observables. And the internal state in the pocket of the adversary will be the particular psi that we defined earlier, so this particular unit vector on the Hilbert space. Does that make sense? Yeah. Great questions, by the way. Thanks for more questions.
So there is a way to break this thing if you could break the claw-freeness.
Correct.
So we're going to have somehow in this proof a thing saying you're either classically either going to be able to break the claw-freeness no matter how, or you have a qubit.
Right. So in fact, we are going to say something even stronger than that.
We're going to see it.
Yeah. We have like 10 minutes left, so I don't know to which extent I'm going to be do a formal analysis. But let me just sort of give you a gist. So we're going to define two anti-commuting operators, and then two operators, and then we're going to say, okay, well, either the prover breaks the adaptive hard-coded properties, or these two operators are indeed anti-commuting, right? And the intuition is that if they were not anti-commuting, then we could break. So sort of the reduction goes like that. Okay? More questions? So yeah, so I don't think I'll have time to do the exact reduction, okay? But I want to at least define sort of the observables, and the definition will be a little bit notation heavy, but hopefully we can extract the right meaning out of that, out of the definition of these two observables. So I hope the goal is clear, like interrupt me now if it's not. Good, so, right, so first of all, well, at the very least we need to define a state psi, right? So psi is going to be the state of the prover right after he committed to the Y, right? So we're going to, run the prover until this particular step of the protocol, and we're going to, take whatever state the prover has and say, okay, this is going to be our psi, okay? So this is going to be our psi, without loss of generality, we're going to say that this psi will be on some register, well, some Hilbert space HP. Okay, so we're going just to define the space where this psi lives as HP. It can be arbitrarily large. Of course, P needs to be, like the number of registers needs to be a polynomial, but just because our prover is assumed to be efficient. Right, so this is going to be our state. Now, now I have to define our two observables. So, right, hopefully I get this correct. Right, so okay, how do we want to define observable? So our first observable will have to have something to do with the fact that we measure, we get some information that we can only get by measuring the particular state in the computational basis. And in particular, the observable that I wanted to think about is the observable that determines whether it is a 0 or a 1 preimage. So is X a 0 preimage or a 1 preimage? That's like sort of the binary observable that we're going to think of as our Z observables. Again, this is like a particular bit of information that we can obtain by just measuring this particular state in the computational basis. So okay, before defining things, I want to make like a few simplification. So first of all, so in general, the general way to model this thing will be sort of say that the prover has this particular state and a given ancillas, which this particular thing lives in some register. I'm just calling it HM, and then whenever the prover is prompted with the query C equals 0, he will apply a given unitary to this unitary 0. And this will define, this bipartite state, psi prime, which now this lives in both registers, right? HP tensor, sorry, in both Hilbert spaces, sorry. And now, without loss of generality, I can always assume that the message, so the reply of the prover is obtained by measuring the register corresponding to this particular space in the computational basis. So this is something I can always do, like just without loss of generality, right? So the prover applies this unitary U0, which is classically controlled on the bit equals 0, and then I'm obtaining the response of the prover by just measuring the appropriate register. So I'm not saying anything particular here. So, and in fact, so I can always redefine a state in such a way that this unitary is actually the identity. How? Well, I just redefine psi to be psi prime. Okay, so I just like sort of preemptively apply this unitary U0 and just say, okay, well, that's going to be my psi. Okay, this is just to simplify the notation. Okay. On the other hand, if I do the same trick with for the measurement, so sorry, for the unitary, which is classically controlled on the bit 1, right, which is going to be the response of the prover if the challenge was equal to 1. Then if I set my other unitary to be the identity, I have to define my new unitary U to be the inverse of U0 applied then, sorry, the whole composition of U1 and the inverse of U0. I'm just shuffling things around, but so again, this is going to be psi prime prime. So the way to compute psi prime prime from psi prime is to undo what U0 did and then do U1. So maybe I made it more complicated than it should have been, but I'm just I'm just calling U0 to be the identity and U1 to be some U, which is actually, well, it's U1 U0 dagger. Okay. If it's that confusing for you, just think of this as just use 0. Okay, so I'm just going to define my observables, and then probably leave it at that. So the first observable, the Z observable, is just going to be the sum over all x in D. So this is just a projection of minus 1b, sum of projectors, x, ket bra, and then the identity. Okay, so this is the identity that acts on the P register. I think I swapped them. Anyway, so let me tell you exactly what this thing is doing and what this function B is. So what this bit B is, right? So this is the observable that does nothing on the register P, which is where the prover stores his internal state. So we don't care about what's happening there, but applies a projection, right, on each particular X, right, on the register that contains the message that the prover is sending. Okay, so this is essentially saying just measure X, okay, like just project on a particular X, and now we have to assign the label of each X, right? And what's the label going to be? Well, the label is just going to be exactly, is this X a 0 or a 1 preimage, right? So if you look at this complicated sum, you can split it in a natural way by just collecting, the same terms, the terms with the same sign to be the sum of two projections, one that projects on all possible preimages which are 0 preimages, and one that projects on all possible preimages which are 1 preimages. Okay, so this is sort of what the observable that we sort of would expect, right, from applying a measurement in the computational basis. Okay. It's a little notation heavy, and I think I also swapped the position of the register, so I made it maybe more confusing than it should have been. So let me just define then X, which is going to be a bit of a challenge, but hopefully we go through that, and then I'm done. Good. So what X is going to be? Well, X is going to be what? Well, let's try to think what this X should model. Well, it should tell, is the observable tells us, is the orthogonal to that particular string which is obtained by bit of x0 XOR bit of x1. So is that, like, was that particular round successful or not? Right. So that's what we want to capture. That's the observable that we want to define. And this is going to be, again, well, sum over all D 0 1 M. And unfortunately, that's the definition of the projector, U dagger. This is the Hadamard transform over this particular M, tensor identity, dagger. Then I'm going below, but this just for space reasons. You should think of this just as a product. And now we have a projection on D, ket bra D, again doing nothing on the other register, and then sort of, well, doing this other thing in reverse, right? So, and I'm going to say a little bit more about this. IPU. Right, so what is this observable saying, right? So this observable is saying, so first of all I have to apply U, right, which was the corresponding unitary to when the prover is triggered with C equals 1, so that's the response of the prover, it just applies U. Then, since I want to measure things in the Hadamard basis, I have to apply the Hadamard transformation to the appropriate register, which is the one that the adversary sort of loads this message onto, right? And then I project onto all possible Ds, and I'm assigning, oh, I haven't tell you what the coefficient is. And I'm assigning the coefficient corresponding to whether that D is valid or not. Well, and at this point you should be able to, I mean, kind of ugly to write, but is this. Right? Good. And just the rest of the unitary is just undoing the thing that I did before. Okay, so you should really think of just projecting onto all possible D, and then assigning that particular a particular eigenvalue depending on whether this D is valid or not. And here I'm sort of swiping the case of D equals 0 under the rug because then it gets even uglier. But this is sort of the observables that we are going to to work with. And maybe let me say just on a high level, 1 minute, what does the proof is going to look like. So we want to show that these observables indeed do anti-commute. And by some algebraic manipulation, at the end we're going to say, okay, either so we're going to reduce we're going to reduce the anti-commutation to a statement about what happens if I apply these two observables in the sequence, right? So like if the things that we said make sense, like if you apply these observables in sequence, right? The first observable should return whatever output is returned, but like the second observable should be completely underdetermined after you apply the first observable. Okay, and we're going to show that that's indeed the case, because if it was not, we would be able to break the adaptive hardcore bit property. In particular, we would be able to sort of obtain simultaneously a preimage of a given Y and a D which is orthogonal to this sort of ugly expression. Good. So I won't have time to go through the analysis formally, but I think this is sort of gives you like the sort of like an overview of what's happening. And maybe let me say one more thing about how you go here from like general purpose quantum computation. So this is just like a very simple task, like just verify whether this is a qubit or not. But it sort of turns out that by using the result or like the recent result about the locality of general purpose local Hamiltonians, then this turns out to be almost enough in order to verify all possible computation. I mean, I guess the classical equivalent of that would be you sort of are able to verify step by step that the computation is done correctly. Of course, it's not. It's more complicated than that. But that's sort of the gist why this is already like a meaningful statement to make, because it's like easy to generalize to multiple qubits simultaneously. I'm over time. Thanks for the attention, and I'm happy to take questions.
So this protocol that you had, the prover has to have, say, if your security parameter is k, they have to have k qubits in order to prove that they have 1 qubit.
Right. I mean, it's probably going to be more than k qubit. I mean, like
a little bit more than k.
Yeah.
So is this scaling somehow necessary?
Yeah. I mean, good. I think like that's a fantastic question. I guess maybe like the question sort of underlying this is like, is this sort of practical towards like proving the quantum advantage or anything? I mean, there definitely needs to be like a scaling in the security parameter in the prover operations. I'm not sure whether you can say that it needs to be like at least k sort of coherent qubits or like error corrected qubits. I'm not sure, but there definitely needs to be some scaling in the work of the prover in the security parameter. It maybe doesn't have to be like k qubit at the same time. Yeah, I'm not sure.
You could ask the prover to work along with a constant number of qubits, or?
Right. I mean, then you're saying the classical work might depend on the security parameter. Yeah. I mean, I'm not sure how I would do that, but I'm also not sure how to rule that out. Yeah. More questions? Okay.
I'm sorry, I don't quite understand. You're verifying that you have 1 qubit gates, right?
A 1 qubit?
Like, you're verifying that you have X gate and Z gates of 1 qubit?
I'm not verifying that you performed a particular operation, like a particular operation on a qubit. I'm just defining the qubit via observable. So observable is sort of my way to, not my way, but their way to sort of define a qubit itself. It's just like you can think of the observable as the definition of a qubit.
Yeah, so like you're verifying the prover has can implement these 2 observables on 1 qubit.
Sorry.
Like, can I say that you are verifying that the prover has a qubit that it can implement these two observables?
Right. So like I can define it, like the way I define the observables. I can say, well, if the prover passes the protocol, like, and it's a little bit stronger than that. You have to say, like, if the prover passes the protocol with very high probability, then these two are, you know, two observables that you can apply on that particular state, and they are well defined, and well, they are both efficiently computable if you have the trapdoor. So I haven't said that, but like the X, for X you need the trapdoor because you have to sort of invert. To apply the observable X, you need to invert the Y, right? So you need to have the trapdoor. But if you have the trapdoor, like both of these observables are you know, efficiently computable and well-defined quantum operation on that particular qubit.
Yes, but these are all single qubits, right? How can we do general purpose computation with them?
Ah, yeah. Well, I haven't gone through that. I mean, it's like, yeah. So right, how to do general purpose computation? Yeah, I haven't told you how to do that, but sort of the idea is that. You won't be able to do general purpose computation yourself, but you're going to be able to verify that the prover has done a particular computation himself, right? And you know, like we know that the verification of a particular quantum computation can be done in a local way, like by just applying like local operators, right?
But local operators, you mean like 2 qubit operators?
Right, 2 qubit operators.
But this is single.
Yeah, but you can generalize it to qubits.
I see.
So I mean that, well, you know, just the simple way to generalize it is you could just repeat this thing sequentially, and you know that you know you can prove that it has like n qubits for the number of repetition that you have. Right? So that's like a simple way to do it.
I see. Thank you.
More questions? Good. Well, if not, thank you very much for attending, and I'm looking forward to see you in the next session of this workshop, which is going to be not tomorrow, the day after tomorrow, Thursday at 9 a.m. And I'm hope you I'm happy to take questions offline. Or thanks for coming. Thank you very much.